All right, welcome back, sustainable students. I want to walk you through some hydro calculations because you have a hydro homework due on the 20th. So I haven't really built that yet, that assignment, but I'll build it right after I make this video. So it'll be a water, pond, dam calculation where you have to calculate the amount of potential energy that's falling from the dam. So we need to go through those calcs. It's a basic calculation. There's a lot of variables, and it's a kind of a potential energy calculation, which we will not get all the potential energy of the falling water. So there's like a percentage reduction, based on the conversion factors that would go on with the generator and everything else. But we can calculate like how much is possible, right? It's like when the sun delivers energy to the earth, we know how much comes, but we can only capture a portion of it. So same kind of thing. All right, I'm going to flip you around. And next. All right, so the first things we have to understand is just some basic energy calculations. So the concept that we're talking about is there's a reservoir of water, right? Maybe a dam or a pipe. A lot of times it's a pipe. Like if it's a big dam, like Bonneville has many pipes running down to generators, big giant turbines. Okay, so as this water falls, it picks up velocity, right? So there's some, usually that velocity is given in gallons per hour. So how many gallons per hour are falling? And we can always look up or collect information about a gallon of water. For example, a gallon of water is 8.34 pounds per gallon. So that right there, the weight of the water is the potential energy, that falling weight, right? When weight falls, there is energy involved and dissipated. If we can capture that, then we can convert it, into some kind of usable energy like we do in hydro systems. So the other thing we need to know is the potential energy is mass times the height that it falls times gravity. And that's going to give it to us in joules. Okay. So if we know the mass, we know how much water is falling. That's the mass. How far it falls, that's the height. So if this, elevation is 30 feet, and let's just say I have 5 gallons per hour, right? 5 gallons of water for every hour would give you, oh, sorry, I should say we'll say every second. I was going to go minute, but then we just have to convert. So I'll say 5 gallons a second. So that's quite a bit, right? 5 gallon bucket every second. It's really not that much, but it feels like a lot if you were to actually hold on to it, right? It would be this 5 gallons, 5 gallons, 5 gallons, right? Just rack up. And again, every gallon is 8.34. So, and if we're saying it's going to fall 30 feet, we can start to figure out like, hey, how much is falling, how far, and gravity. And the easiest calculation for that is to get it into grams. So, and to do the metric system. This G is gallons. I should probably write that. So this is going to convert to 5 times, because every gallon is 3.78. It's going to be 5 times 3.78 to get us our kilograms. That's important, kilograms. Because this mass is in grams, this potential energy mass, right? All right, so we're going to take our 5 and we're going to get 3.78 and times. So that gives us 18.9 kilograms per second. Okay. So that would be also what? 18,900 grams per second. And if we take that 18,900 grams per second and we multiply it by the height of 30 feet, sorry, let's keep our units correct. So I'm going to say this is meters. Okay. Because the equation is much easier in meters. So if we can get meters, grams, second, and then 9.81 is the gravitational constant. That's what this is, 9.81. So we got mass, height in meters, mass in grams, and G. All right, so let me run that number real quick. All right, so I just double checked, and this mass needs to be in kilograms. So I was incorrect down here. This would be 18.9 kilograms. All right, so we have kilograms, mass. I should have known that because of the whole concept of newtons, but that's right. And then this is 9.81 kilograms, right? This is kilogram meter per second squared. Kilogram meter per second squared, right? That's the gravitational constant. So all of these units are going to combine to calculate out to what we call a joule. So this equation gives you joules, and joules is a energy packet, okay? It is not time related, but it's just like an energy unit. And if you put it over seconds, like joules per second, you get watts. And this is typically what we want to know is, hey, how much energy could we produce in watts, right? So we can get it in joules pretty easily, but normally we want it like per second. And that's this whole per second thing, right? That's this. It's telling us how many are coming per second. So the per second doesn't actually go in the equation. This first thing is just mass. So this is mass, height, and gravity to give us joules. All right, so let's see what we get. Our mass that's falling per second. So this is a per second calculation because our mass is per second, right? But we don't need to put that in. We just put the mass in. But we know it's happening over time. All right. 18.9, enter, 30 times 9.81 times. So that gives us 5,562. 5,562 joules. And it is like our 5 gallons falls every second, right? That's our velocity. So it is per second. So that is a watt, which means we have the capability of producing 5.56 kilowatts. Right? That's the possible energy creation from 5 gallons of water per second. 5.56 kilowatts. Okay. Now a kilowatt, that's a kilowatt hour, right? So the conversion happens within this. You go to watts and kilowatts. All right, so that's pretty interesting. 5, that's a lot of falling weight. That's if you could capture it all. In a hydro system, obviously we can't capture it all. In a larger system like a dam, they do a pretty good job capturing it all. So I think I have a PowerPoint, yeah, that shows kind of a dam setup here. So you can see these are the tubes that run down, water levels up here, you know, that water level might be, 100 feet kind of thing. So this water load is falling, and kind of the cut view, and I know this is a little blurry, but This is internal tubes. The one that you saw here is kind of internal and external tubes. But then you can see the water falls and comes down, and they're just literally blowing it by a turbine, right? And then there's large gearing that's gonna spin a generator up pretty fast. So this is a slow rotation, then to get it to a high rotation, a large sprocket, and then a smaller sprocket. So these turbines in dams, they spin pretty slow on this level, right? But then when they're actually spinning a generator up, they spin pretty darn fast to get high RPMs. So I have a generator here that I'll show you. And it'll just give you an idea of, how these things work. So we have basically our potential energy. That's a possible 5.56 kilowatts if we could capture it all. This is kind of a small generator, but it gives you an idea. Like it fits on my piece of paper, and you can see with my hands how big it is, right? You can see that the rated voltage is 24 volts. So this would have to be converted if we wanted to use it on the grid to 120. It needs a rated speed of 2650 RPM, so 2,650 revolutions per minute. If you divide by 60, you get revolutions per second, but still, that's booking, right? That's like the revolution of a car. Our cars run at, 2,000 or 1,500. So this is like a car in height or a low gear. So it gives you a rated current of 3.7 amps. And then the output wattage is only 250 watts, right? But with gearing, our little flow of 5 gallons per minute could easily produce enough torque to spin this up if you had the gearing done correctly. So anyway, I just wanted to show you that. What you're going to do in your homework problem is calculate a flow over a dam. So look for that, and good luck, and let me know how it goes.